Okay, let's get started. Okay, so today our content is about logistic regression. Okay, still remember what we have learned last week? We learned linear regression, right? Okay, um, just to have some recap, right? We said that there are two major tasks in business analytics. The first thing is to do exploration, right? The second thing is to do prediction, okay? And when we are doing prediction, actually we have two types of prediction to do, okay? Okay. What we mean by prediction? We means we have some predicting variable, and we want to use this predicting variable to predict an outcome variable, right? In business, we have some repeated event of uncertain outcome, right? Repeated event, right? Each of this data point is an event, right? Uncertain outcome is mean that there is a target variable just of our interest, right? And that variable, like, it change, right? It's uncertainty there, right? So because the outcome of our interest is uncertain, so we want to utilize some predicting variable to predict that outcome, right? This is called prediction, right? And we say that we have two types of prediction, right? Does anyone still remember the two types of prediction? Depends on the data type of the outcome, right? We have two different types of prediction. Prediction, louder, please. Last week we learned about how to predict. Yeah, numeric outcome, right? When we want to predict numeric outcome, usually we use a regressing method, right? They are, as I have told you, that there are hundreds of methods can predict a numeric outcome. That we learned the most basic one, which is linear regression, right? So linear regression is one of the methods that we use to predict numeric outcome, right? So today we are going to predict the other type of outcome, which is categorical, okay? Or when we are predicting categorical outcome, actually the model will predict the probability of each alternative outcome, okay? To make it simple, usually we start with two different outcomes, yes or no, right? Sick, no sick, right? When you do a penalty kick, you can in or not. You score or you not score, right? So the easiest, the most basic categorical outcome is kind of what we call binary outcome, which means that there's one way or the other, okay? So when we are predicting a binary outcome, we are actually predict the probability of each alternative outcome, okay? So usually we will encode outcome as 0 and 1, right? So we are predicting the probability of y equal to 1, okay? So this type of regression is called the way that we operate is always the same, right? We have data, and we use the data. The data need to have some predictor, and you need to have some historical outcome, right? In the history, you have the outcome, you have the data. So you use this data to build a model, and then you have some new data, right? You can throw in the data to the model so you can predict the outcome, right? But with this new data, you do not know the outcome, right? So you want to use the model to predict the outcome for you, right? So the difference between last week and this week is last week our outcome are numeric, and we are using linear regression to do the prediction. And this week, our outcome is actually binary or categorical, okay? And we are using logistic regression to predict the probability of outcome equal to 1, right? Okay. Any question? So that is basically what we want to do today, okay? As I told you, that when you predicting numeric or categorical outcome, they are like hundreds of methods to use, right? And in our course, we only use the two most basic method, right? The linear regression, logistic regression, they are very basic. So they are simple. So they are easier to understand, okay? But don't worry about that there are so many methods that you landed, right? Because in the environment, because in the modern environment like in R, right? All of the methods are actually encapsulated in packages, okay? So as long as you learn one method, you basically apply the same procedure to all of the models, right? So although it's not our scope to cover many machine learning or artificial intelligence models, the application of that model in terms of business analytic, in the labels of business analytic, they are all the same, right? So that's our philosophy, okay? So linear regression, a quick recap, right? Because logistic regression is another kind of linear model, right? Linear regression and logistic regression, they are what we call linear model, right? Which means that we are predicting Y, right? That we are using what we call we are using a kind of vector combination, right? We are using this linear combination. Say we have X, right? And for each of the X, we have a corresponding coefficient, right? We multiply the X with the coefficient and then add intercept, right? So it's kind of like very simple mathematical form, right? Use a very simple mathematical form to predict the expected value of Y, right? The Y hat is not the actual Y, right? It's the expected value of Y. So we use this simple form to estimate the expected value of Y, okay? But we know that the expected value would not be the same with the actual value, right? So there will be error, right? So when we have a very good model, the error is small, right? Then we will have a good prediction. And when we have a bad model, the error is big, right? So that is basically what we have learned last week, right? Last week we also learned about something like this, right? See, this is the basic operation of the linear model, right? Since we have data, right, then if we give the data to the method, right, this is a method, LM is the method that we use, right? So we give the data to the method, and then the method will build a model for us. What we mean by a model is actually it would find B0 and B1, right? It would estimate a set of coefficients that produce the smallest error between the prediction and the actual data, right? Okay. So linear model, if you the benefit of using linear model is actually very easily we can visualize, right? We can visualize the data each of this point is a data point, right? So, and where is the model? In this chart, where is the model? The blue line, right? The blue line is the model. See, the data we have is actually like scattering, right? A little bit scattering. And another thing is that, see, actually, as long as you have a model, right? For every given x, for every given x, 4.5, 4.55, 4.5559, okay? As long as you know x, you actually can estimate y, right? But the data point is kind of finite, right? You don't really have a data point for every x, okay? But after you build a model, you actually can predict the value of y for every given x, isn't it? Right? So you actually fill the blank, right? In when you visualize it, it becomes a line in the plan, right? Okay. And in this line of plan, you can see that they are arrow, right? This is the actual value, and this is the predicted value, right? As I say that the model actually predict the expected value of y, and the expected value and actual value, they are different, right? So different is called arrow, okay? What this method do is it try to find a set of coefficient to minimize the error, right? And that is automatically encapsulated in the LM function call, right? You don't need to know the detailed mathematics, okay? What you need to know is you give the data to the LM method, and it actually find a set of coefficient to minimize the error between the expected value and the actual value of y, right? That's the thing. So, and we have some way to kind of evaluate the accuracy of the model, right? If the model is very good, the data point will be very close to this blue line, right? Okay, and if the model is not so good, then you will see a large error there, right? Okay. People might ask that then how good is good enough? But that depends, right? It really depends on the data you have, and depends on the question you are asking for, right? Some question will have a very high precision. Some prediction will, in its nature, have a high level of prediction. Some model is not so precise. Okay, that's kind of review what we have do last week, right? The reason that we do that is because logistic regression are, sorry, let me go back. This is linear regression, right? So this week we are doing logistic regression. So basically we'll do the same thing, right? We will explain how to build a model of logistic regression, how to interpret its coefficient, and how to measure the accuracy, okay? And how to use logistic regression in the business decision, okay? That's what we want to learn this week. Usually, making decision out of the logistic regression is not as easy as you think, right? It's a little bit complicated. So this week we can only maybe cover this part, and this will be the topic for next week, okay? Now, let's compare the model a little bit, right? Before that, I think I should take a look at this first. What we mean by logistic regression, it is kind of it is another kind of linear model, which means that it, like linear regression, it starts with this linear combination. Okay, it is still predicting y, and it still use this form of this mathematical form. We call it a linear combination. Okay, which means that we have a vector of x, right, and we have a vector of coefficient. We multiply coefficient with the predictor variable and add them up, right? So this is called a linear combination. So it always starts with a linear combination. So still, you will have a coefficient for each of these predicting variable. Still, you want to like multiply coefficient with this predicting vector variable and calculate the sum. But the problem is that the sum cannot predict y directly. Now, your y only have two values, right? 0 and 1. I told you that logistic regression is only good for binary type of outcome, which means that it only have two outcomes, by, no by, right? In or out, male or female, right? Black or white, right? So only have two outcomes, right? Sick, no sick, right? It's broken, it's not broken, right? So logistic regression is kind of like predicting the probability of something, right? The probability that this customer will buy next week, right? The probability that this patient will survive for 3 years, right? The probability that Germany will win. What is the game last night? Germany with Spain, right? So it can win, it can lose, right? But actually, the soccer game is not. You cannot predict the outcome of a soccer game by logistic regression. Cannot, right? Why?
Because there are three outcomes.
Yeah, there are three different outcomes. They are tied, right? So that is a bad example, right? So as long as you have binary outcome, you can predict it by logistic regression. The problem is when you do this linear combination, it can be anything, right? I mean, the value of this linear combination can be very small, right? It can be very large. But the probability is always a value between 0 and 1, isn't it? Right? So you need to do some transformation, okay? The largest difference between logistic and linear regression is that because the outcome, what we are interested is actually the probability of y equal to 1, right? This is what we are going to predict. But this linear combination cannot predict that directly. You need to do a series of transformation. Okay? If we denote the sum of product as f of x, then you need to you need to use this transformation function. This functional form, we call it logistic function. Okay, so after you get the f of x, you need to apply the transformation to transform the sum of product, the linear combination, into the probability of y equal to 1. Okay, you get me? Okay. Let's take a look at this graph. This is the f of x. Okay. I mean, still, when you build a model, the method will tell you a set of coefficients. Okay. Still, you use this set of coefficients, right? Multiply with the x, with your predicting variable. Still, you will get a value. We denote it as f of x, right? It's a linear combination of x. Okay. But this linear combination of x cannot predict the probability directly. It needs to go through a transformation, okay? And that transformation function is called, this function is called logistic function. It looks like this, okay? This is f of x, okay? And this is the probability of y equal to 1, okay?
Some of a part of the PPT is cut, like we can't see the whole slide on.
Sorry?
The left side of the PPT gets cut, like on all the three.
Oh. How can we do that? It looks strange, right? The resolution are I think yeah, that will have problem, right? I don't know what happened, but it looks like the resolution is not compatible any longer. I'll try to. This is more like it, right? So I have to basically do the same thing here. Try to fix this one. Okay, let's get back to work. Now, what we say? We say that for logistic regression, the linear combination no longer predict y directly, right? You need to use this. You need to use this transformation. You need to use this transformation function, right, to transform f of x into the probability of y. You see that in the vertical axis, here is 0 to 1, right? Okay, so this is the probability, right? So whatever the linear combination is, with the function you will transfer into 0 and 1. When the f of x equal to 0, the probability is what? 0.5, okay? And when the linear combination is very large, it's larger than 5, then the probability is always very close to 1, right? And when the linear combination, the value of the linear combination is smaller than -5, the probability of y equal to 1 is like very close to 0, right? And it's not linear, right? I mean, this transformation by itself is not linear, okay? Although this equation, this mathematical form looks a linear function, but in order to get the probability, there is a nonlinear transformation, right? To transform the entire real value range into 0 and 1, okay? But actually, it's only sensitive between like -5 to 5, right? Okay, except 5, it's already 1, right? And lower than -5, they are like very close to 0, right? And when the f of x equal to 0, the probability will be equal to 0.5, right? This is basically the difference between logistic and linear regression. You get it? Get it? Okay. So let's take a look at this one. So this is the modeling and predicting code. Okay, when we want to do a linear regression, right? We first of all we want to fit the model, right? You have a data, and you have the model spec, right? And you call it LM, then you get the model, right? And you want to examine the model, you use summary M1, right? It's model 1. Okay. If you want to do prediction, now if you want to predict the expect value in the training data, you don't need to give it new data. Okay? I mean, if you only want to see the prediction value for the training data, you simply do predict model, because the training data is already inside the model already. Okay, so you can get the y hat predictive value of the training data this way. But usually we will predict new data, right? So besides the model, we also give the new set of predicting variable, right? And for each new data point, you will get the predicted y, right? This is the way to do a linear regression. Okay. Well, very similar procedure apply to logistic regression. See, instead of calling LM, now we are calling GLM. Okay, and there is an extra argument called family equal to binomial. Okay. Because GRM is a generalized linear model, it can build a lot of model type. I mean, besides logistic regression, it can build a lot of different type of model, right? So when you want to build a logistic model with GRM, you need to specify family equal to binomial. Okay. So this is the two different, right? First difference is this is GOM instead of LM. Second is you need to specify family equal to binomial. Okay, that is the way to build a logistic model. Of course, in this case, your Y need to be encoded as 0 and 1. Okay. Now, examining model is the same thing, right? You use summary, okay, and you still use the predict function to do the prediction. But when you do the prediction, you need to add an extra argument called type equal to response. Okay. Here you call predict. You give the model, you give the data, right? But here when you do a prediction, you need to give the model new data. Also, you need to put in this argument. Okay. So doing logistic regression is a little bit more complicated, right? So you need to add, you need to remember to add in this argument when you do when you fit the model. You always need to remember to add this argument when you are doing the prediction, okay? But the process is basically the same, right? Processes are basically the same. Get it? Okay. Okay. So so let's get into some real example to get you familiar with the model building and the predicting process. Okay. Today we have three notebook to use, right? The first one I hope that I will have time to go through all of these three notebooks today, okay? But after I go through all of these three notebooks, it is basically only cover this part, okay? These things, I think we will need to cover it next week, okay? So if you go to the unit 10 folder, you will see two things, right? PowerPoint and the zip file. And as usual, if you unzip the file, you have a folder, okay? Unzip the file, you have a folder called 10 Logistic Regression. Go into that. Go into this one, okay? And let's take a look at 10A first. Again, in the beginning, there are some code chunks to simply preparing the data and examining the data. Okay. The categorical model or probability model. Actually, when we say categorical model, are actually the same as probability model, because predicting category is actually predicting the probability of each alternative category. Okay, so they are the same. Okay, so there is a name usually in some discipline they call it classifier, because they are picking one of the class of the categorical outcome. And actually classifier predict the probability of each category, right? So logistic regression is the simple classifying method, okay? That only predict binary outcomes, okay? So usually binary outcome are encoded as 0 and 1. and we use logistic regression to predict the probability of y equal to 1. Okay, that is what we have covered. Now let's start with a simple example. Okay, we start with a simple example with only 3 variables. Okay, let's read in the data. So I built a demonstration data set called D, right? Only have 3 variables, okay? Y is the outcome variable. As you can see that it already been encoded as 0 and 1, okay? And x1, x2. So I want to use x1 and x2, these 2 numeric predicting variable, to predict the probability that y equal to 1. Okay. Now, usually the first thing that we get the data, when we get the data of binary outcome, the first thing we want to do is we want to see the number of 0 and number of 1, right, within the data, right? So this is kind of like, if I if I do a table on y, I'll see that the number of 0 and number of 1, right? If I do a mean on y, what does this mean? When I do mean of y, right? What does it mean? What is 0.25 imply? So y is binary, right? So y are 0 or 1, okay? So when I take average of y, it's basically the probability of y equal to 1, right? Isn't it? Right? So if I do not build any model, right? I simply want to guess the probability of y equal to 1, right? Without any model, I can actually use this one, right? Okay? If I do not have any x, right, and I want to predict the probability of y equal to 1, I know that I should predict it as like 0.25, right? So the reason that I want to use x to predict y is because that if x and y are correlated, right, so I will have a better prediction. First of all, my prediction will be point by point. They are different, right? This is just average, right? And with the model, I want to predict every individual, isn't it? Right? So this is kind of like, for the entire training data, this is the average. But the reason that I want to build a model is because I want to predict every individual point, right? Isn't it? Okay. So, but it's always good, right, to see the average before I look into the individual, right? Okay. So that's why in the beginning of the case, when we get the data, we always examine the number of y equal to 1 and also the fraction of y equal to 1. Now we are going to build a model. As I told you, building model is so easy in our environment, right? It's just like, this is our data, right? And this is our model spec. Y is our outcome. X1 and X2 is our predicting variable, right? And we want to build a logistic model with GRM So we need to add this argument in the function call, right? And then the function call will return a model. And this is a name that you give it of your own choice, okay? So you get the model, and then you can see the model summary by calling summary, see? And as you can see that the summary of logistic regression are very similar to laws of linear regression, right? The most important thing is actually the coefficient, right? So let's get back to here. This is linear regression, right? You have a digital combination. You have this linear combination. You use the linear combination, the value of the linear combination to predict y directly, linear regression. But for logistic regression, still they are using the value of a linear combination to do prediction. But it cannot do prediction directly. You need to do some transformation before you can get the probability of y equal to 1, okay? But you don't really need to worry about too much about this mathematic things, right? Because in R, all of this mathematics is already encapsulated behind the function call. So as long as you know how to use this function call, everything is fine, okay? Okay, let's go back to notebook. So you know the coefficient, right? And actually, this is the model, right? If we want to extract the coefficient, you actually can extract the coefficient out of the model and put it in a name, B, right? So when we do this, we will have a vector of coefficient. Okay, so let me do that. When we execute this line of code, the coefficient is here, right? But if we want to extract this value, we can do this, right? We can actually execute this code. And then you'll see that there's a vector here, right? B is a vector, and this is the intercept, B0, B1, and B2, okay? B1 and B2 is the coefficient corresponding to x1 and x2, right? Okay. So you can get the coefficient. And then you can calculate the linear combination, right? This is just basically the mathematics. If you want to calculate the probability by yourself, you can do that. Usually you don't need to, right? You just call the predict function. Then the predict function will calculate the probability for you, okay? But as long as we are in R, right? So we can like learn a little bit more about the basic idea about logistic regression. So you have we know that we can do the value of this linear combination by this code, right? Now, one, if for example, if I want to evaluate the probability of y equal to 1 when x1 equals to 3 and x2 equals to 4, right? So x1 equal to 3, x2 equal to 4, right? So what is the probability of y? Then we need to follow this transformation. If you want to do it by hand, okay, this is what you need to do, okay? First of all, you calculate the value of this linear combination, right? So this is basically a multiplier of vector, right? Coefficient multiplied by 1, right? B1 multiplied by 3, B2 multiplied by 4, right? Isn't it? Now, B0, B01, B0, 1, 2 is here, right? Is this vector. Because we already extract that in this vector, right? So now I want to multiply B0 by 1 because it's intercept, right? And I know the value of x1 is 3. So I multiply B1 by 3, multiply B2 by 4. So in R, right, this is vector multiplication, right? And do a summary. And this is the value of f of x, okay? But the value of f of x is not a probability, right? It's not the probability. As you can see that, what you have is here, right? You need to do some mathematical transformation to transform it into a probability, okay? And in order to do that, we need to introduce a few terminology, okay? Sorry, it's 10 o'clock already, so let's take a break. And then when we get back, we will learn a little bit more about the mathematics behind logistic regression. Okay. We'll be back at 10 after 10. Okay.
For our homework assignment, is it from Unit 1 to the end of Unit 3?
Sorry?
For our homework assignment, that is due next Sunday,
Yeah.
we have to do this course. So, like, it says finish Units 3 to 1. Like, which part do we have to do? Just this one?
Yes, just this
Just
one.
okay, thank you. So not the introduction and the first.
But actually, this one is just a very short video. Okay. This is actually the assignment for this week, right?
Yes, yes, yes.
So this is only a very short video.
But
Okay.
we don't need to like do the rest.
No,
Uh,
you only need to do
like we don't need to do unit 1 and 2.
no. You only need to do Unit 3, and basically just this one.